So this is what you turned in, and what you actually turn in is this. And we're gonna need, you need to know what you used for the moments coefficients, you know, that 1/24, 1/14, 1/10, and you need to know the lengths. And so I didn't have to jump back and forth between screens. I just copied that information here. So those were the coefficients you used and the lengths. And for this student, what I did was I just looked on the spreadsheet that was turned in, and I could get these lengths and coefficients right off that spreadsheet. Okay, so if you remember for bar cutoffs, it's you H, have any extra bars. If you do, E, establish where you no longer need them. L for development length, LD. And then P, practical ACI details. So first of all, this is what most of you had for the beams, 2 number whatevers. And so there are no extra bars. There's nothing to cut. So the rule is at least 1/4 of the bars of the positive, oops, have to go from support to support. So you can't cut them. You have to have at least 2 bars for the stirrups. So there's no cutting. They just go all the way. Now, excuse me. So I think you can get bars up to 60 feet long, because that's the longest flatbed trailer that you can pull on the freeway and get off the off-ramp. I think it depends on like what city you're delivering to and what the off-ramps are in that town. But I know we've received 60-foot long. Oh, say again? I didn't hear that. What was that?
Nothing, I forgot to mute.
Oh, okay. So anyway, you don't have to make that 21 feet, 18 feet. What I'm saying is, you could get a 60-foot bar, maybe go over 3 foot of the spans, but I don't care. In a project, you could just turn it in like that. But you can't really cut those bars. There's only 2. Similarly, there's none to cut here. You can't cut those, but what you do need to figure out, and several of you have asked me this, is how long do you make those bars? And that's what we'll answer today, okay? So what you need to remember are it's 2 number 5 bars, and the moment diagram was 1/24. In this case, if you come into so if you have when you're coming into a spandrel beam, it's 1/24. I can't remember what it is if you come into a column, like 1/16, I think. I can't remember the number offhand. Okay, so it's 1/24. This one is 1/10. That one is 1/11. Okay? And you also need to know the lengths, 21 feet and 18.5 feet. Okay, and so here's the graph. Okay? So I've scanned it. That's the page from the book. And how this works, it's the moment diagram. So it's half of the moment diagram. That's the worst case positive moment diagram. That's this. Okay, that's this. This is the worst case negative moment diagram, and it's that. Okay, and then what this is, this axis, that axis is the percentage of your length, the decimal of your length up to half the span. So that's 0 all the way to 0.5 L. Okay, so it's this, L times L times L. Okay, that's what it is, times, those are L's. Okay, this axis, okay, so let me blow that up. Let me try it, there we go. It's what percentage of the MN you can cut off. Okay, so if you cut off 100% of the MN, then you're down to 0 moment. This is how far you need to go. If you cut off 50% of your MN, this is where you go. So remember how we did, you found the reduced MN and you draw a cross and you see where it intersects? This is what it is. You draw a cross and you find the points. Okay. It depends which moment diagram you have, and it's the 1/24, 1/16, 1/12, etc. It depends on which one you have. And the only thing is, I would have done it like this: 100, 90, 80, and that's the percentage of your maximum moment. But how Dr. Dolan did it, he's doing it by how much you subtract off. So 30 means I subtracted off 30, meaning I'm at 70% of my MN, of my maximum. Okay, so that's the one kind of hard thing about this, is it's going from 0 to 100 instead of 100 to 0. To me, it would have been easier if you had done it like this. Okay. What percentage of the maximum are you at? But instead, he did 1 minus that, so how much you can cut off. Okay. And in his book, what he argues is that if you cut off 30% of the steel, you're cutting off 30% of the MN. But it's not exactly true, because T goes down by 30%, but A changes slightly and Z changes slightly. And in the book, he goes like, oh, don't worry about it. If you have 30% less steel, just use 30% less moment. We're not going to do that. We're actually going to calculate how much moment you decrease when you cut the bars out. Okay, so this is how you do that. Clean this up. So the first thing is that we are looking at the 1/24 line, because because of that, we had the 1/24 moment over there. Okay, so we're going to look at the 1/24 moment, and we want to know, we want to cut 100% of the steel. We want to know, where does it go to 0? Okay, so we want to know here. When it gets, to me, when it gets down to 0, what he says, when you cut off 100% of the moment. Okay, so 1/24, it intersects, if you look, every line here is 0.01, 01, 02, 03, 04, 05, all the way to 0.1. So I think that is at 0.092. It's just totally my eyeball on that curve. So remember 0.92. So there you go. That's how long you make that bar. 21 inches from the face of the support. Okay, let's do the 1/10 and the 1/11. Okay. Oops, I'm trying to move it with my computer. There we go. Okay, so the 1/10, that's 0.28, and the 1/11 was 0.024. If you look at the scale, let me just. Okay, the 11 is at 0.24 and the 1/10 is at 0.28. Okay, so 0.21, 0.22, 23, 24, 5, 6, 7, 8. So that's, I just read it off the graph, 0.24. So just remember the 1/10 is 0.28 and the 1/11 is 0.24. 28 and 24. 28 and 24. Okay, so 0.28 times 21 feet. So that's how long that bar is. You add it all up, 71. And we're assuming those columns are 18 inches wide. We'll have to fix that once we get the column size. But assuming they're 18, I'll add that all up. $143 inches. I would just make it 12 feet. Okay. Okay. So that's that. That's established. I'm getting a piece of thread stuck in my hand. Okay, so now L, check the development length, okay? Another super handy thing in this book, so let me, so another super handy thing in the book, he has a table of development lengths, so you don't have to do any calculations. Can't find it right now, but just believe me, there's a table back here. I'll find it just a minute. And this book is a bestseller for practicing engineers, a lot because of these tables in the back, so you don't have to do any calculations. Oh, here. So he has a table here, and it just lists the development length if you know what bar size you have, what F prime C and what Fy. And so it's super handy. Oh, that was compression. Here's the tension. So this is the development length and tension. Okay. So yeah, I'm just, it's not that hard, the equation, but I'm just lazy. So I use this table a lot. Okay, so we need to check the development length now. Okay, so the development length for a number 5 bar, I have it here. Okay, so we have to check the development lengths. Oh, let me transfer. Oh, I forgot to add. You have to add D. So let me copy those things down again. 21, 71, and 44. That's the theoretical cutoff points. Oops, I got share, sorry. Share screen. So those distances I calculated, sorry. Those are the theoretical, and remember you have to go an extra D 12 bar diameters or L over 16. And by the way, D is almost always greater than L over 16 because remember D is about L over 10 or L over 12. Anyway, D was 10.5 inches, 12 bar diameters was the number 5 is 7.5. So it's, we're gonna add D, 11 inches. Sorry, I forgot that. So that's E, establish the theoretical, and then add the extra. And you have to add the extra 11 inches, okay? And now L, check the development length. And this is what I'm saying. I was just too lazy to calculate the formula. And that's what came out of that table I just showed you. So it's just 38 times the bar diameter. And it depends on the table. It asks you, is it a top bar or a bottom bar? But remember, to be qualified as a top bar, you have to have more than 12 inches of concrete below the bar. And this thing was only, how tall was that? The whole beam was only 13 inches deep. Oh, did I read that drawing wrong? Were these beams 18 inches deep?
Yes, they're 18.
Oh, bummer. Okay. So, so the top bars, you have to multiply by 1.3. Let me do that. Okay, so the development lengths are 31.2 and 37.1. Okay. Okay, so this is number 5. LD is we have 32 inches. This is good, just barely. These are number 6. That's definitely bigger than 37. So these are good. So the final lengths are now 32. Those are the final lengths. I was off by 11 inches earlier. Okay, the last thing to check is that's only 16 inches into the column, because you need a 1.5 inch cover, and you'll have basically a 1/2 inch hoop or stirrup in the column. It's like a stirrup, but it goes on all 4 sides like a square hoop. So you only have 16 inches for your hook, and is that enough to develop the hook? And so if you watched all those videos, that's the equation for the development length for the hook. So 60,000, 55 and square root of 4,000, and then you have all these factors. It's not epoxy coated, so it's 1. This R has to do with confinement. I'll show you the slide for that, but it comes out to be 1. I can't even remember what O stands for. I have slides for each of these coefficients, so we'll go over them. The one I want to point out is the concrete factor. It's FC over 15,000 plus 0.6 if you have less than 6,000 PSI concrete. And so that comes out to 0.87. This is lightweight concrete, which we don't have, so it's 1. Okay, so let me show you all the coefficients, where they come from. Oh, and it can't be less than 6 inches or 8 bar diameters. Okay. Lambda, lightweight concrete, 7.75 regular, 1. Epoxy, 1.2, regular, 1.0. And many of you on your sheet at the very bottom, you have phi mn over mu equals like 1.12. You get to divide the development length by 1.12 because you have extra steel. Okay, this one, this confinement. This has to do with how much of the transverse hoop steel you have. If that steel is more than 40% of the hook steel, it gets to be 1. Or if you look at the top view of the beam, we have 2 bars. If that space is more than 6 bar diameters, it's 1. And it was more than 6 bar diameters, so it was 1. Okay. And this one was if you had cover greater or equal to 2.5 inches or 6 bar diameters, it was 1 for number 11 and smaller. And so we had more than that, I think. So we'll just call that 1. Okay. And there's the concrete one. So anyway, I did all that and I came out to a development length of the hook of only 7.5 inches. We have 16, so that's fine. Okay, so that's how you do the bar cutoffs for the beams. Okay, you just find those lengths on the graph, add D, and make sure it's greater than the development length. The girders are a little more challenging. So here's a girder design. Because the girders had bigger loads, sometimes you had more than 2 bars. And so this example I picked, there were 3 number 8s on the left, 3 number 8s on the bottom, 6 number 7s over there, and 4 number 8s over there. And this student had a nice spreadsheet that had all the phi mn's at the bottom. So I just copied those down. Just make sure that when you do this, you do mn. Make sure when you calculate A, you're using the correct B. You know, for the positive moment, it's B effective. For the negative moment, it's the B web. But anyway, and here are all the dimensions, okay, here. Okay, so now H, have extra bars. On the left side, there are 3 number 8s. I'm gonna cut 1 of them. On the bottom, there's 3 number 8s. I want to cut 1 of them. Okay, so at this one, you have several choices. You could cut 2 of them. You could cut 4 of them. I think that's your only choices if you want to keep symmetric. So I'm going to see if we can cut 4 of them. And then 4 number 8s, can you cut 2 of them? Okay, so this is what I tried. Okay. I'm only going to do 3 of them, and this part is the same. Like ones you don't cut, how long do they go? Is just like the one I just did, the previous one I did. So what we're gonna add on this one is, can you cut the bars? Okay. This student had a really nice spreadsheet. So I want to know, if I go down to 2 number 8s, what's the new fee MN? But I was too lazy to do the calculation. But the student had this really nice spreadsheet already. And most of you have this, where you check at the end, if you have 3 number 8s, what's the fee MN? Well, I didn't want to calculate it, so I just typed over in the spreadsheet 2 number 8s. And there's the fee MN. Okay, so all I did was I just typed into the spreadsheet the reduced number of bars, and I got the new fee MNs. Okay. So it was 302, it went down to 204. Okay. And this was using 1/16 now instead of 1/24. Right. Look at here. Okay. And by the way, this student in the spreadsheet, it had the denominators at the very top of the spreadsheet. That's how I knew what they were. It was 312. It went down to 209. It was 449. It went down to 156. Okay. Now, I guess what Dr. Dolan said is true. When you go from 3 number 8s to 2 number 8s, you're dropping 33% of the steel. The MN drops 302 minus 204 divided by 302. That's 32%. So there's no difference. 3 number 8s to 2 number 8s, that's drops 1/3. That's 33% drop. 6 number 7s to 2 number 7s, you're dropping 2/3 of the steel, and it drops 65%. So I guess what Dr. Dolan said is correct. If you just take the percentage of steel you drop, that's pretty close to the percentage of MN you drop. Okay, so let's do this. So on the 1/16th graph, we're gonna drop 32% of the MN. On the 1/16th graph, I'm going to drop, and you can see that this is not the most exact thing, so the difference between 32% and 33%, I don't think is that big a deal. Okay, to me, that looks like 0.042. So the theoretical cutoff point is 0.042 ln. Okay. Okay, so let me draw that here. The proposed cutoff point is going to be that plus D. Okay, it's going to be at 46.1. Okay. So the question is that more than LD? And if it's not, you have to extend it. I'll let you figure that out. Let's find that point. That looks like 0.143 to me. And remember, from there to the theoretical of the other one has to be greater than LD. Okay, we need to check development length. These are number 8s. On the top. I'm lazy. I'm just gonna look it up for you in the table. I can't even remember the page number. Page 752. I'll also scan this page for you. Page 752. Or I'll just make a spreadsheet for it. Okay. Top bar, number 7 or larger, with minimum stirrups. Okay. So the development length is 62 inches. Okay. 46 is no good. Well, the diameter of a number 8 bar is 1 inch. Okay, so you wanted to cut it at 46, but you can't. It's at 62. Okay. That distance there That's going to be close. Okay, so the bars you are not cutting go to 86.1, and the bars you are cutting go to 62. Okay, so I'm just gonna say, I'm gonna round to the nearest 3 inches. The nearest 3 inches to 86 inches. Okay, that's how you do that. Let's try the positive steel. You had 3 number 8s, but you want 2 number 8s. You're gonna cut off 33% of the positive steel, and this was the 1/14 moment diagram. 1/14 positive, cut 33%. Oh, that's a long way to go down there. I'm gonna just read the numbers off. This is to me, that looks like 0.283. That's 112 inches. Okay. So this one's that's 112 inches there. Okay. You need to add D that way, right? Okay. So let me redraw this. Remember, 112. Obviously not to scale. Let me try that again. Okay, closer. Because we're measuring from the maximum, so we need to know the distance from the middle to the point. I'm going to add 29.5 to that. Is that greater than LD? Okay, so for a number, what are these? These are number 8 bars on the bottom. So number 8 bars on the bottom, I'm gonna use this table again. bottom bar number 8. So the development length is 48 inches. That's good. 115 is way more. Okay. The next question is the ones you're not cutting to here. Or not a big, that's it's bigger, right? That's bigger, so that's definitely greater. Okay. So we're fine. I'm gonna round this to the nearest 3 inches, 115 inches. It's 9 feet 7 inches, so 9 feet 9 inches. Okay. Okay. And that's how you do this. Okay. So the key to this is I would do the homework first so you understand how, you know, the theoretical and the proposed before you try this. And then when you try this, the key to this is to get your theoretical cutoff point, you just figure out what percentage of steel you're dropping off and just go across. Okay, so this can be we proved that percent steel cutoff is the same as percent MN reduction. Okay. One last comment that is outside the scope of this class, but it's pretty cool, is this. Up and down. What is he talking about? And so if you're really, really clever, which some of you are, but it's too late now because you've already designed the beams. Okay. Let's say you had 3 number 8s, 3 number 8s, and 3 number 8s. But eventually you're going to cut off to 2 number 8s and 2 number 8s like that. The 1 bar that you're cutting off, you can do this. I'm going to use green. So if you're really clever, that 1 bar you're cutting off on the top and the bottom, you can make that bar look like this. And so that 1 bar starts as a top bar, bends down to a bottom bar, and bends back up to a top bar. And then so if you're clever, you could do that. And it takes a lot of thinking. And that's where these graphs come in handy. So basically what you're doing is you're gonna come here, with this 33%, add your D, come here, and then I'm gonna shrink this. And then you're gonna bend it like that. And that's why he's made this graph to look like this. So you could figure this out just by looking at the graph. And this is a super, super handy graph. But at the time, it was just way too much to explain. And it might be confusing you right now, but that's what this graph is for. So you can say, oh, I'm gonna cut X% on the top and the bottom, and I'm gonna bend it down or bend it up. Okay. And so, you know, in the US, our moment diagrams are upside down. negative moment is on the bottom, but the steel is on the top. And so in other countries, this graph is upside down, and that green line looks exactly like what your bars look like. It's exactly how the bars would bend in your beam. So anyway, that's total bonus. And there was no way I could have explained this at, this was like 10 weeks ago when we were learning this. But now that you know everything, if you could go back in time and you picked, so if you picked the same size bars, tops and bottoms, and the same numbers, you could, I don't know if it's even worth it to do this. And really, I don't think this is a standard practice in the US. Oh, my screen has stopped tracking my iPad. I'm moving the iPad and that's not moving. Anyway, that's bonus. That's what this graph's for. And I'm going to try and reproduce this graph on Excel. But in the meantime, I'll just scan it so you can have it. Okay, so that's how to do bar cutoff for the project. And I'll post the link to this so you can have it right away with the password this time. And then eventually I'll turn it into a VidGrid video. And this is the end of bar cutoffs, and next topic is deflections. What I think we'll do on Monday is during this time, I'll walk through the exam. I'll show you the exam and we'll talk about what it is. And then I'll assign it, and then you have 24 hours to do it and turn it in. There'll just be one shear problem and one bar cutoff problem. And since there's only two problems, there'll only be 150 problems for me to grade. And it takes me about 5 minutes a problem. So that comes out to just 12 hours of grading. The other test took me about 20. So what I'm saying is I think I can grade exam 2 before they've extended the deadline for you to decide letter grade or SU. So my goal is to have, if we can do exam 2 on Monday, I can get that graded before you have to decide if you want SU or letter grade. The only thing is, because there's only two problems, don't mess up on one problem. Okay, don't mess it up. And they'll be not like what I just did. This is it'll be like the homework. Okay, it'll be just like the shear homework and the bar cutoff homework.